Okay, so we're gonna continue with the motion section we've been talking about. Now, we already know some basic equations. One is the equation that relates distance or displacement, velocity and time. So velocity is given by displacement divided by time. We can modify this and we can rewrite this as displacement equals velocity times time. So this equation works if you want to find things like average velocity or the total distance. So this gives you this, and the previous works for average velocity. You cannot use this equation if the velocity is changing, means if there's an acceleration or a deceleration or slowing down. If the velocity is changing over time, this equation does not work. So you need to remember that only for constant velocity. Right, so that's also important. Alright, so we also talk about how to find acceleration. Acceleration is velocity change divided by time. So units again, just to remind you the units, this will be in meters per seconds. Acceleration meters per second squared. So acceleration is velocity change, the velocity difference divided by time. Now you see in both these equations we are relating only three quantities, right? This one has velocity, displacement and time. This one has acceleration, velocity and time. We don't have an equation that relates all four variables. We are dealing with four things: displacement, velocity, acceleration and time. So now what we're going to talk about is a set of equations that relates all four of these variables. They're very useful calculating things involving motion. The first two equations are also important, but the next equations I'm going to discuss, they kind of look little complicated because they have too many terms in them, but really useful. Once you start working with them, you'll find that they're really easy to work with as well. So let's take a look at these. Alright, so the first one we're going to talk about, equation number 1. We have velocity final equals velocity initial plus acceleration times time. Velocity final, velocity initial, acceleration times time. You can write it this way also: velocity final equals velocity initial, instead of I you put O, plus AT, the same thing. Just to keep things clear, I'm gonna quickly delete that second one I wrote, but just keep in mind instead of I you can use letter O as well. Okay, equation number 2. So equation number 2 is distance equals velocity initial times time plus half times acceleration t squared. The second equation says the distance traveled is equals to the initial velocity times time plus the second term, half times acceleration times squared. Third one, velocity final squared equals v initial squared plus 2 times a times distance. Fourth one, this one not really useful. The first three are the most useful equations because they relate all four variables. But the fourth one is just a simple thing, just the average velocity. Velocity average is velocity initial plus velocity final divided by 2. Just how you take the average, you add the two numbers, divide it by 2, you get the average, right? So these equations, sometimes you might see, for an example, the second one written as equals to initial, so this distance final, initial plus v initial t plus half at squared. Same thing for this one, v final squared equals vi squared plus 2 times a times, instead of just the distance, the delta distance, the difference between x final and x initial or xi. These equations means the same thing, and most of the time, almost all the time, when you use these equations, you'll see that initial distance is always 0. We always start from the origin of the coordinates, like our starting point is always 0. So therefore this number, this term, most of the time, almost all the time, this is 0, this is 0. So it doesn't matter, I mean, this having and this f really is not that useful, so we can get rid of that, So you see this whole thing is 0, it goes away, this goes away, like that. So it becomes this simple equation again, right? So you might see these x0 terms, xi terms in your textbook. Don't worry, most of the time you can make it 0. Not most of the time, all the time you can make it 0. Alright, so these four equations are called kinematic equations. Kinematic equations, or equations of motion. Using these, we can actually, these are very useful, we can solve a lot of interesting problems. So we're going to talk about few examples. Okay, so let me erase this and move on to few example problems. Alright, so oops. Okay, don't need that. Alright, so I'm going to solve few problems. These are, again, you can find these problems in your PowerPoint. Let's start with number 1. Problem number 1. Now when you solve these problems, it's a good idea to write down all the information, so it makes it more clear to you. So write down the information, add a diagram. Diagrams are always super helpful. It makes things more graphical, you know. If you are a visual learner, it will help a lot. It's easy for me to understand, like if you are working on a problem like a homework problem, and if you show a diagram, it makes more sense to me also, so I know what's going, what's your plan. Okay, so some instructions. So I can say write down the information in points, in point form also add a picture. Okay, so this is just information. Alright, question number 1. The first problem it's about acceleration of a car. It says, how long does it take a car to cross a 30-meter wide intersection after the light turns green? The car accelerates from rest at a constant 2 meters per second squared. Okay, so we have a car. So let's say this is the intersection, right? So the road comes in, there's alright, how do I draw this? So here's the car waiting at the intersection, it's at rest. Okay, so initially our V initial is 0. The intersection is 30 meters wide, so from here to the other end of the intersection is 30 meters. What else? So when the light turns green, when the time starts, it's gonna go forward, crossing the intersection. It's gonna accelerate, it's gonna increase the speed at a rate of acceleration of 2 meters per second squared. So the question is, how long does it take? What's the time? If the time here, if it starts from 0, what's the time over here when it is passing the other end of the intersection? So let's see what information do we have in hand. We have V initial 0, V final we don't know. V final means over here, V final we don't know. We know the distance it traveled, 30 meters. We know the acceleration, 2 meters per second squared. We don't know the time it took. That's the question, how long it's going to take. So these are the information we have, right? Initial 0, final we don't know, distance 30, acceleration 2. Question is, what's the time? So now what do? We go back and look at those equations. So if you can scroll back a little bit, you'll see the 4 equations, or you can go to the PowerPoint, you'll see the equations. So what is the best approach? Think about it for a second. Which equation are we going to use? V initial, V final, distance, acceleration, time. So by looking at the information in hand, I'm going to go with equation number 2, which says x equals VIT plus half AT squared. Distance equals V initial time plus half AT squared. So now I'm going to plug the numbers. Distance 30, initial velocity 0, times time I don't know, plus half times acceleration is 2 times time squared. 30 equals, this whole thing becomes 0, right? 0 times t, doesn't matter what the time is, you multiply it with 0, it becomes 0. So 0 plus half times 2 times t squared. This is a dot here. 30 equals, this is 0, half and half becomes 1, t squared, right? So this gives me time equals square root of 30, which is something like 5.5, I believe. Let's see what the answer is. Square root of 30 equals to 5.47. 0.47 seconds. Alright, as a rule of thumb for these calculations, I want you to keep 2 decimal points regardless of significant figures and all that. Throughout this course, let's keep 2 decimal points at least for the final answer. You don't have to leave more than 2, more than 3, like 4 decimal points, 5 decimal points doesn't make any sense. We are not hitting that much accuracy levels in these calculations. We don't need to. This is about a vehicle moving across the intersection, so having an answer for 2 decimal points is more than enough. So we found the time 5.47 seconds. Okay. Alright, now let's think about, we can add something to this, right? Now we found out it takes this much time. How about finding the velocity at this point? It's not asking the question, but just because we are interested, what's the velocity when it is coming to the other end of the intersection, right? In the beginning it was 0, now it's speeding up across the intersection. What's the final speed? So let's give a try. V final. What do you think a good equation we can use? Now let's see things we have in hand. We have V initial 0, acceleration 2. We already have the time which we calculated, 5.47. So using this, we can very easily use this equation. V final, V initial plus 80. 0 plus 2 times 5.47. So this is like 10.9 something, I believe. Meters per second. Velocity final. By the time it reached the other end of the intersection, the velocity is 10.94 seconds. Okay, I believe you are getting this. We can always solve more problems in class. Alright, so let's move on to another problem. So I am going to erase this. Okay, let's look at the second problem. This is again from the PowerPoint. Second one says an airplane lands with an initial velocity of 70 meters per second. So the airplane is it's landing, it's coming to the runway, it's coming in with a speed of 70 meters per second and then decelerates at 1.5 meters per second squared. So it's gonna decelerate, it's gonna slow down at a constant rate of 1.5 for 40 seconds. What is its final velocity? How far it travels during this time? So let's see. So let's write down things in hand. So here comes the airplane. So the wheels out. I know it's a really not a good diagram, but I think this will help. So it's coming in with a speed of what do we have, 70 meters per second, and then acceleration. Now this time it's slowing down, right? So we need to keep that in mind. This is a negative number. This 1.5 meters per second is negative. It's slowing down, 1.5 meters per second squared. And then so after 40 seconds, we don't know whether it had come to a full stop. It could be, maybe it's still moving. So let's call this V final. This is what we need to find out. V initial. So let's assume that it's already on the runway. It's moving horizontally. It's not still flying, right? It's on the runway. It's going at 70 meters per second. So let's say this is our V initial. Next question. The question is, what is the final velocity? V final. So the things we have. Question number 1. V final. Question number 2. Number 2. How far it goes. What is the distance? So let's say this is the point A where it was going at 70, and this is point B after 40 seconds. Distance A to B. So these are the 2 questions. So let's write down the information we have in hand. Let's see. We have V initial equals 70. We have acceleration equals negative 1.5. We have time equals 40 seconds. Second squared, meters per second. Questions, V final, and also distance. These are the 2 questions. By looking at this, first equation looks like the best option. V final equals V initial plus AT. Now this is what you need to practice. By looking at the variables in hand, by looking at the information in hand, you need to figure out what should be the best starting point. You can start with other equations also. It will work, but it might take a lot more steps to get to the answer. So you see 3 things available here. We have VI, acceleration, and T available to us. So this is what we are looking for. So equation 1, kinematic equation 1, directly gives you the answer. So that's the easiest approach. So V final equals VI is 70 plus, remember, acceleration is a negative number, 1.5 times time is 40. We have 70, multiply this, and this negative multiplied, and there's a positive here, it becomes a negative number. 1.5 times 40 is 60. We have 70 minus 60, 10 meters per second. V final, it's still moving, hasn't reached to the full stop, still moving at a slower speed, which is 10 meters per second. Question number 2. How far it goes during this time? Now some might think that think of using this equation, distance equals V times time. I told you, please remember this equation only works if you have a constant velocity, right? Here we don't. We have a deceleration. The speed is changing, it's reducing, so we can't go with this. We have to go with one of those kinematic equations. So which equation can we use? We have initial velocity, we have acceleration, we have time, now we have final velocity as well. We can think of this x equals VIT plus half AT squared. This works because we have initial velocity, time, we have everything we need, and the equation gives you the distance. Or we can use this also, V final squared equals V initial squared plus 2AX. We have V final 10, initial we have 70, 2 times acceleration times distance. This also gives distance, this also works, but this one, X is already in the left hand side, so I'm just gonna go with this one. So distance equals 70 times 40. V initial was 70, time is 40, plus half times remember the negative sign. 1.5 40 squared. So we're gonna need the calculator. We might need the calculator here. I'm gonna continue here. X equals 280. 70 times 40 is 280, plus, actually this plus becomes minus, so let's erase this. Alrighty. So here we have half times negative 1.5, so that becomes negative 1.5 times half is 0.75. And 40 squared, 40 times 40, 1600. Okay, now I'm gonna need the calculator. 800, actually it's 1200. 800 minus 1200. Let me just double check whether I'm right. 0.75 times 1600. It is 1200. So this gives you 1600 meters. So the distance it traveled is 1600 meters. Okay. Alright. So on PowerPoint there's another question. I want you guys to take a look at it, give it a try. We will discuss this during our discussion sessions. Okay.